back to the shop. Today we've got a really cool relay on the bench. This is the Basler BE1-50 This is the B model. There's a bunch of different variations of very, very similar relays brought to you by Basler. This is a solid state relay. So if we can see here on the board, it's actually got a PCB with, surface mount components, little analog chips and stuff like that in there. So this was very popular in the sort of in-between period between what we have now with the modern microprocessor relays and way back in the day when we had electromechanical relays. This was sort of bridging the gap between the two. So technology was improving. We've got better accuracy. We've got solid state components, no moving parts, things like that. It's a little bit less susceptible to damage, wear and tear, things like that. But there's no display, there's no communications to it, there's no metering in it. It's all solid state. You test this almost exactly the same way that you test a electromechanical relay, except it's all solid state. It's all stuff on the board. It's capacitors, resistors, transformers, stuff like that, but there's no rotating disc. So a pretty good step in the right direction, a much more modern take on a protection relay than the IAC relay we looked at whenever I posted that in the past. One of the big selling points when this initially came out in 1992 was that you could get this relay, or a very similar relay brought to you by Basler, in a drop-in replacement model. They could build these to fit the existing electromechanical relay cases from Westinghouse, the CO cases, and from GE, the IAC cases. You could get one with the exact same pinout as the existing electromechanical relay and just drop in something, and now you've got selectable curves, you've got a more accurate time curve, you got more accurate instantaneous pickups. They're a huge improvement, and you didn't have to do any rewiring, you didn't have to do any new engineering, didn't have to add anything crazy to it. It wasn't a huge retrofit. You could just put a better relay in the same exact socket and be up and running in no time. So these were really popular when they came out. You're still going to see them all over the place nowadays. They're still very popular now, but as we'll see, solid state relays from the early 90s, the early 2000s, they do have some issues. There are some, and they're mostly component failures that we're going to run into now. And when we get into this, we'll take a look at it. But there's a reason we don't typically install new solid state relays anymore, and we're going more towards the SELs, the GEs, the microprocessor based relays. So without any further ado, let's really dig into it, and we'll look at some of the details, some of the things that makes this really cool, and start testing it. So this is our magnificent Basler BE1 case. The only thing noteworthy on the front cover is that we've got this little target reset button right here. It's not even spring loaded. It just pushes on the target reset right there. If we spin around to the back of the case, we'll notice one nice thing about this is they've taken the liberty to print the circuit diagram or print the terminal descriptions right on the back, so you know exactly what you're doing. And then we also have a description of the curves, the selectable curves. So that is nice because we've got selector switches right here. I'm not sure if this is going to come across on camera very well, but we've got different curves that we can select on the front of the relay. Now this is a huge improvement over the old style or the older electromechanical relays, because to change the curve on this guy, I need a whole new relay. I gotta buy a whole new unit, put a whole new unit in this bucket. If I want to change the curve on this, boop, there's my setting. There's no messing about. To change the taps on the old electromechanical relays, we talked about this in a previous video, you have to unscrew this little guy, and it's really finicky. You got to move it over and set it wherever you want, and then you have to retest it at the new curves, and setting the time dial is a little bit finicky, and it's not always super precise. On the Basler, on the BE1, those are our settings. I can set this to whatever I want, as long as it's within range, but I can set this to whatever I want right here on the face of the relay. So huge improvement. One thing that is a little bit different because we don't have a rotating disc. We can't actually see it physically move. We have a pickup light, a little LED that'll come on when we're above our pickup threshold. So that's kind of nice. Very similar to our IAC and the CO as well. We've got different contacts. We've got a contact for the time overcurrent element and the instantaneous element. And we've got an aux contact, which is both, but it's not rated as high of an amperage. So that's just something to be aware of. But the aux contact will tell you if it tripped. So that's kind of nice. The pinout on this one is different than the IAC that I have, but you can get them in several different configurations, several different types that will have different pinouts. The CT circle will be on different places. If we look at the relay itself, this has regular service paddle. It's just almost identical to the one we had for the IAC. And it works pretty much the same way. I mean, it gets contact to all of the pins on the back of the case through the service paddle. And very similar to the IAC, we also have a spring. Man, you're not gonna be able to see that at all. We've got a spring-loaded CT shorting bar in the back. So as soon as you take the service paddle out, CTs are shorted back there. So that is kind of nice. That's really all there is to talk about on here. Oh, one more thing. Most of the settings, 75% of the settings are on the front here. There are several that are on a dip switch way in here. So we need to be aware of these. On this one, my board is from I think 2000 or 2001. I believe this relay is. I could be wrong. I'm not 100% sure on the dates on this, but they call this, and that's switch 8.1, switch 8.2, switch 8.3, switch 8.4. We'll look at the manual in just a second to talk about what those are. Oh, one other thing while we're in this camera setup. This was the test switch paddle, or the test paddle that we used in the IAC relay. It fits exactly the same. Go figure. Same case, same test paddle, everything works great. Note that on this, if you just came from that previous IAC video, I have to move where the shorting bar is because the CTs are on different pins on the back of the case. The red knob right here, which is the inside one, if I were to put this here, I would be connected to the bottom, which are the pads here, which is why obviously on the case side where my CT is connected to, when I push this in, I'm going to open up the shorting spring that's on the CT terminals in the bottom of the case. So I put this shorting bar across where my CT terminals are. On the red one, so we short on the case side. The black little studs here connect to the top of the test paddle, which are obviously continuous with these terminals here. So that's the relay side, that's the top side. So when I connect up my test set, the case side of the CT connections is shorted, and then everything else will be connected onto the black studs. So there you go.
Okay, I want to talk really quickly about the manual. So this is one of the relays that you would not be able to test this without the manual. It makes no sense the way that it's set up. There's even like parts of it that even the manual itself doesn't really make sense unless you read the whole thing. Again, this isn't a super complicated one like some of the SELs that we looked at that are multiple hundreds of pages. This is only 64 pages and most of them are pictures. So one thing that I want to skip to, if we go to page 45 on this particular manual, so we see this is relay differences. The long and short of this is on BE1-50-51s that were made after about 2000, 2001. The switch here is called switch 8. That's that dip switch that I showed you just a second ago. Switch 8 is taking the place of switch 3. Just be aware of that. They call it switch 8 on this model. On older ones that predate 2000, it'll probably be called switch 3. older versions of the manual, so if you have like an old version of the manual and a newer relay, you're going to be so confused looking for this little dip switch that just doesn't exist. So be aware of that. So what does switch 8 even do? As we can see here, so I have this one, BE1-50, 51B107. Just tells you what style case it is. The S1 case is the GE style case. If switch 3-3, or the third little dip switch down, is selected, our instantaneous overcurrent trip has a 0.2 second delay. So it just adds a delay on the instantaneous pickup. So something to be aware of there. It can do different things on different relays. The 200s, so BE1-50/51B- 202, 205, 203, whatever, 207. The 200s, that switch changes the curves from a CO shape curve to an IAC shape curve. So just be aware of that. It's just a different mathematical model to come up to the same, essentially the shape of the curve is what I'm trying to say. There are some other things that the other 3 switches on switch 3 do. And they're talked about right here. So switch 3-1 is 50 or 60 hertz. It's going to be off if you're in Norte America like I am. Excuse me, from 60 hertz. So switch 3-2 is selects additional delay for the instantaneous element, so we can add more delay onto it. Switch on provides an additional instantaneous delay of 0.1 seconds. Switch 3-3, this is a 100 series, we're on the 107. Switch 3-3 on adds an additional 0.2 seconds of delay on the instantaneous. So just be aware of that. If 2 and 3 are both off, the instantaneous is instantaneous. There's no intentional delay on the closing of that. Just something to be aware of. Switch 3-4 provides selection of either instantaneous or integrating reset characteristics. So if it's off, as soon as the current goes below the pickup or the tap value, it resets automatically. If switch 3-4 is on, it has a timed reset similar to our electromechanical relay, where like when I was doing the time overcurrent test, you have to push the dial all the way back, or push the disc all the way back to reset. If that is switched off, it will be a lot easier to test because it will reset automatically. It's just something to be aware of there. So like if it starts timing but hasn't tripped all the way, it'll wait a while. It has like a timed characteristic until it starts over from 0. So it starts from a cold start essentially. So just something to be aware of on that. When I'm making my test plan, I typically record the position of those switches and record what all that means. This manual's pretty good. It has a picture of the front of the relay and then explains what all of those functions do. So it's got a little, oh, this is what this is. This is what that is. Cool. And then it's actually got a board picture, so it can help you find, depending on what style of Basler relay you're looking at, it can help you find where your switch 3, or in my case, switch 8, physically is on the board. If you don't know what you're actually looking at. We do have a sample, like a schematic of what your typical trip circuit would look like. So terminal 3 is the common point on the trip circuit. Obviously, terminal 6 is our time over current target, or our time over current trip and the circuit for the target. Terminal 2, as we saw on the back, is the instantaneous trip output. So you normally would gang those two together, your jumper 2 to 6, and then run that to the trip coil for your breaker. So all that makes sense. Page 37 is the one that we want to look at for our tolerances. They have it weirded wordly. Thanks. They have it worded weird in some of the other parts of the manual, so make sure that you actually come straight to the operational specifications chapter to get the exact accuracy. So in this case, we have the 5 amp unit. It's plus or minus 2%, plus or minus 25 milliamps, so 0.025 amps. Accuracy for the pickup or dropout, so the time overcurrent pickup dropout is 5% below the pickup. So it'll pick up, latch in, and there's like a little bit of hysteresis there. It takes another additional 5% to ramp down to get the pickup light to drop out. Our timing accuracy, plus minus 2%, plus or minus 25 milliamps, plus the 1 cycle plus minus 2%, right? So it takes into account that there's additional sources of error because it's timing and it's the pickup, right? Or it's timing and the amount of current. So they have to play off of each other. That's really all they're saying. If you're testing one of these and it's timing within plus or minus 1 cycle, within plus or minus 2%, so stack on top of each other, right? That is, so it would be plus 1 cycle plus 2% or minus 1 cycle minus 2%. That's our, I'll show you how we actually calculate that, but that's our actual tolerance in there. If it's within that, it's good. If it's like slightly outside of that and your pickup's off by a little bit, you can sort of like fudge it and say, hey, we're off, but like we're still kind of within tolerance based on the manual. If it's really, really far off, fail it. These are old relays. The owner of this relay understands that this thing from 1992 or 2002 or whatever it was actually installed. They understand that there's a good possibility it's going to die soon. So, and then so that's our timing accuracy, and then I don't think it explicitly states it, but it's implied that our instantaneous pickup needs to be within plus minus 2% as well. So that's our tolerance. What else we got? At the end of the book, it actually has graphs of all the different curves. So that's really cool. It's good to know. If for whatever reason the software that you're testing this with, or if you're doing this super manually and you don't have the software, you can actually go to the back of the book and eyeball out, hey, this is, at 2 times my pickup, it should trip at roughly this amount of time. At 10 times my pickup, it should pick up at this amount of time. So kind of cool. It's worth noting. Most relay manuals nowadays don't have that because they just expect that you know how to calculate out the curve. I am currently hooked up to terminal 3 and terminal 6, which is my time over current element. And then I've got my current inputs on 8 and 9, which would be my normal CT input. And just good practice, I've got my little CT shorting bar on the case side of that test switch. I'm on a bench, so it doesn't necessarily matter, but just be aware of that if you're doing that in the field. That's what you want to see. It's what you want to look like. So we're going to make a new test plan over here in Protection Suite. So our relay device. Oh, hello. What are you getting mad at? So over here in Protection Suite, this obviously you're going to want to put in all of the information that you have. BE1-50/51 Bravo TAC 107. Device manufacturer is Basler. Model is going to be the same thing as that. Obviously fill in as much of this stuff as you can. Just a new test plan. Name your test plans, guys. It definitely does help if you're coming back to this again and again and again. We'll call this one maintenance 2024. So our protection settings, like I said, most of our protection settings are going to be on the front, but I always will record switch 8.3, sorry, switch 8.1, switch 8.2. In my case, they're all currently off. So I just record that on solid state relays that have additional dip switches, additional things that modify the settings. Just record that. It's going to make it a lot easier if you ever have to come back to this and, somebody questions your report, somebody questions your settings, something like that. Like having a record of what it was currently set to, especially those little dip switches, it helps a lot. Trust me. 3.6, our pickup, our time over current pickup, or our tap, is 3.6. That is 3.6 amps. The curve, I believe that is set to M. So I'm just going to note that here. I don't know if I'm going to be able to get that to pull in automatically, but we'll take a look at it. Time dial is 4.9, so I'll call that dial, and we'll call this 4.9. Instantaneous pickup is 2.2. Oh, sorry, that is 22. So we got to be careful. This is ones and tenths. So,
4.9, 3.6, and then the one on the very end is tens and units. So that one is 2.2, that's 22 amps on the secondary. Now, if we had switch 8.3 or switch 8.2 enabled, we would need to sum together the delay. Switch 8.2 is a 0.1 second delay. Switch 8.3 is a 0.2 second delay. So we need to sum those together. In my case, we're just going to call this instant delay of 0. I typically don't test the delay. If there is an intentional delay, we test it. If there's no intentional delay, we typically don't test it. So first off, we're going to need to verify our pickup, right? Exactly the same way we would have to do for the IAC that we just tested. So let's take a look at that. Steady state tests. In this case, I can't get a hardwired pickup out of the unit. I have to use the LED. So we're going to do a manual test. This is going to be our time over current pickup. Time over current pickup. Our expected value here is the tap. Our offset current will be the tap times, 90%. We said our tolerance out of the book was page 37. Tolerance out of the book for the pickup is plus minus 2%, plus minus 25 milliamps, milliamps. In this case, I'm hooked up to output IA on my test set. So it'll be source IA, that's that first current channel. It's always good to double check that your sources line up with what you are expecting out of the state summary here. And so this is going to go in terminal 8, come out terminal 9, or the other way. It doesn't necessarily matter. There's no polarity here. Okay, so that looks good. So we're going to start 10% low. Our current limit in this case is going to be tap times 110%, 1.1. Our delta current, we want to go in pretty small steps. So I'll do 0.5% steps, equal sign to enter a value here. So those will be 0.005. That's 0.5%. So every time I hit the up arrow key on here or click on the little up icon on Protection Suite, it will ramp up by 0.5% of our tap. So at most, we'll have to go up like 40. You have to click the button 40 times to go up. Just be aware of how big those steps are and make sure that we're starting on a. So here's my tolerance, right? My plus minus 2%. I need to start either above or below that, and then shrink into where I expect my my relay to operate. In this case, I expect my relay to operate at 3.6. That's our tap value. So we're going to start 10% down, and I need to ramp up until I get into my tolerance band. So my test points over here, this is where I set my tolerance, is plus minus 2%. If it's a little bit outside of that, we do have that plus minus 2% plus minus an additional 25 milliamps. I'll show you how to add custom tolerances in if we need to do that, but I hope we don't need to do that. Our connections for the trip sense. It's terminal 3 to terminal 6. Just be aware of that. I always like to make notes on how I'm actually measuring my my input from the relay. So all that looks good. Let's go ahead, turn the test set on, and we'll give it a shot and see what happens. So we are connected to the instrument. We're going to hit run test. And again, what I'm going to do is I'm going to hit the up arrow key on my keyboard until the little red pickup light, until our little red pickup light comes on the relay. And then I'm going to hit manual sense, and that's going to record the value that the time over current picked up at. There we go. Our little red LED came on at 3.618 amps, which is half a percent, or about one of our creep steps up. So, that looks good. I'm totally happy with that. Next up, now that we've done our pickup, right? That's the first test we need to do, verify that our time over current element is picking up the right amps.
I need to verify the timing of that time over current element. So we're going to go steady state tests, and Protection Suite makes this super easy. You should have a fairly similar one on whatever software you're using if you're not using Adobe. This is going to be our time over current trip plot. You can name it whatever you want. Try and be consistent. That's my big thing. Now there's no characteristic here, right? What we need to do on Protection Suite, we go Protection Functions. So we go back to Relay Device tab and then Protection Functions. We have to add modify. This is our overcurrent element. It doesn't really matter. We'll call this BE1-51. BE1-51. It has Basler. It actually pulls this name in from the nameplate data over here. It's kind of interesting. Just be aware of that. We called our curve M. So we're going to go Protection Functions. Now, I'm not sure. If I just type that in, does it bring it up? Hey, it does. Look at that. BE1-851M. I believe Basler is pretty consistent on all of their curves. If that's the wrong M shape, it actually might be this one, BE1M CO moderately inverse. They have the same one, the same M curve in several different places. It should be this one. I think the 851, it's just a carbon copy of the existing moderately inverse curve. So doesn't really matter. Pick that, makes the most sense. Again, this auto lookup thing. So if you have the setting saved as a variable in the protection settings, which I do here, we can pull it in that way, or you can manually select the characteristic here. Sometimes it's just easier to manually select the characteristic. Just be aware of whichever you chose, especially if you're copying this test plan over and over and over again. Just maybe double check that if you're copying to a different style of relay. Okay, so our next one is, we want this to be our tap value, right? Because that's our pickup. You can either do it in multiples of your CT tap, which makes no sense. I don't like doing it that way, or in secondary amps. Most relays are going to tell you what the value is in secondary amps. So tap, and that was 3.6. Again, that's our time over current pickup. This is our dial setting, was 4.9. That looks good. We don't have any adders or anything like that. Nothing weird going on here. So we'll go back to here. Now we've got our characteristic available on our time over current trip plot page, or our TO. What do they call this? TOC PLT is the Protection Suite macro for it. So BE1-51 moderately inverse curve, and again we're going to go IA. So that first current channel out of the test set, that's going to be our action state. So everything that happens over here only happens to this A channel. And we're reading our input back to the relay. The digital input to the test set is the actual output contact from the relay, if that makes sense. I always use multiple tap. We go to our test points, hit the little down arrow. We get 3 lines here. Anita says you have to do 2 points on the curve. I always do 3. I don't know why. I just always do it that way. And Protection Suite's smart enough to calculate those curves for you, which is fantastic. Our timing, we said, was plus or minus 1 cycle, plus or minus 2%. So what I typically do, because I'm lazy, is I'll put in 2% first, and then if it's less accurate than that, I'll make a custom tolerance function that we can plug those numbers into here. In this case, I think it'll work with 2%. And another note here, if you've got that electromechanical reset thing going on, you'll need to wait a super long time between tests. So just be aware of that. Offset current duration, we can set that to 0. Time is going to be 1.2 times expected. Reset on ours, I'll leave that at 0. There's a little bit of delay time. There's a little bit of lag between the end of one test and the start of the next. Let's fire it up and see what happens. Yeah, 14.5 amps for 2 seconds. Yeah, everything will be fine.
And so again, we are injecting on 8 to 9 and reading our inputs off of there, our time overcurrent inputs off of 3 to 6, which is our 51 element. And there we go. That one looks good to start off with. That's nice. Let me move my stupid fat head out of the way so you can see the curve. Sweet. Wow, that was perfect. First try and everything. Heck to the yeah. So go ahead and save your... Every time after I mess with my test plan at all, I always save it. Oh, it's got a dash in it. Or a slash needs to be a dash. There we go. Try that. Okay, so what's up next? So we've done our time over current pickup and our time over current timing test. Next, we should do our instantaneous. So what I will typically do for that, there's a couple different ways you can crack that egg. You can either just manually ramp it up. In this case, it's what, 22 amps. It's not that much for my test set. It's not that much for the input of the relay. The better way to do that, I think, would be a pulsed ramp. So we pulse the current on and then turn it off, and pulse the current on a little higher and then turn it off, and then pulse the current on a little bit higher, and on until it trips. We'll do that. It's a little bit less wear and tear on all the parts. Instant pickup. So our values here, hit enter to go into formula mode. That should be, is that not what I called it? There we go. Our offset current, so this is our start value, right? 0 amps is fine for that. We'll offset for 15 cycles. Doesn't really matter. Quarter second. I do all my timing in cycles. I'm weird. If you don't like doing it in cycles, do yours in seconds or milliseconds. But I don't know. It just always seems to work for me. I don't have a reason to change. Our initial current. So this is where we're going to start at. So this is our first pulse. This is going to be instant times, remember, it's something bigger than our tolerance band. So 10%, our tolerance band is plus minus 2%. If I start 10% low, 0.9 times my instant setting, that should work fine. So let's do that. Our pulse duration, this relay is going to trip really, really fast. So I'm not super worried about it. 5 cycles is generally fine. Our weight, I'll almost always do a quarter second for that, 15 cycles. Our delta current, so how big of a step are we going to take? Again, I like 0.5% for this. So that's 0.005. And that's not the tap, that is the instantaneous setting. There we go. So our instantaneous setting is 22. 1% of that would be 0.22 amps. So each pulse increases in magnitude by this amount, the height of that. So each pulse is going to go up by 0.11 amps, if that makes sense. Now our current limit, where do we want to stop at? One thing that I've found, if you're making test plans that you're going to copy and paste over and over and over again for a bunch of different relays, don't just go off your setting, because sometimes like your instantaneous setting is going to be like 90 something amps. So if your current limit is 90 plus 50%, 90 times 0.15 or 1.5, the test set's going to get really angry at you. The software won't let you start the test. So sometimes if you want to just make sure you're not going to overload the output on your test set, you can set this to like a fixed amount, 30, or if you're using a transient output, you can put 60 right there, and that will keep your test set from outputting too much current. That's just something to be aware of. You set this at 30. If it runs up to 30, you're not going to hurt anything. So 30 amps, that should be fine. And then our tolerance on this one, again, is plus minus 2%. So let's go. Oh, the other thing, our connections are going to be different. So this is terminal 3 to terminal 2, according to our schematic. 50 is 3 to 2, right? So our 50 element, our instantaneous overcurrent element, is 3 to 2. So I need to move where my connections are.
All right, beautiful. So this should just work in theory. Fingers crossed. And we can see the pickup light blinking because we're going to, 19 amps, then 19 plus a little bit, 19 plus a little more. So it blinks and it's off for a quarter second at a time. So everything looks good there. That's Gucci. It's perfect. I love it. Sick. So what's up next? Our target. Yes. So these are, you have to test them different than you test electromechanical ones. On the electromechanical ones, I have the option of like physically pushing the disc closed and holding the main contact closed while we push current through the ceiling contact. I don't have that here. We can't do that. So what we need to do is actually push current through the relay until it trips and then start our DC current through the target to pick up the little target, right? And in this case, they're not mechanical flags. They're the stupid little magnetic ones. And, well, we'll see in a second why I have this relay on my desk. It was free because it doesn't work. Okay. So we need to do both, right? Because there's two targets on here. We've got the time over current target and we've got the instantaneous target. So we need to test the operation of both of those. So I guess we'll start with the, how do I want to do this? I think the best test for this would be the go, no go test. Because I'm not trying to say it's a functional test. I need to visually see that the target picks up, and I'm not gonna get an input back to the test set, right? I don't have an input that the test set can see. The test set doesn't have eyes. So what we need to do is we're gonna inject our current the same way we did before. We're gonna do, so instead of having the amount of current that we're injecting into the CT input being our action state, I'm going to have a fixed amount of current. How long did that take to trip? So if I go to my time over current plot, it tripped 7.2 amps in 250-ish cycles, right? So I can do, what do I need to happen? I need the trip circuit to close, right? I need this output contact to be closed so that I can inject current from terminal 6 to terminal 3, if that makes sense, to pick up the target. So what we're going to do is I'm going to trip it by injecting, 10 amps for 240 cycles, something like that. It'll trip, right? So we're going to do 10 amps for, so our offset current, our action state is actually going to be a different one. It's going to be channel B. So I don't necessarily care about that, or I need that to be 0. Our offset duration, we said it was 240 cycles, which is 4 seconds. Our test current, in this case, if we look at the manual, they say it needs to operate at 1 amp. Where physically is that? Target test. They tell you, hey, do the thing, make sure it times out, blah, blah, blah. Set the voltage to provide a target current of 1 amp. Okay, so we're going to just whack 1 amp in there and see if it operates. This is a little bit different than the way that we did the electromechanical one, but we're doing essentially the same function. Another thing to note, in this manual, they tell you how to test it, but they tell you how to test it in a stupid way. They're like, hey, you need to put these exact settings in and push this exact amount of current in, and that's dumb. That's dumb. Don't do that. You need to test the settings that the relay is actually configured to, because if it doesn't work the way that it's intended to be used in service, it's useless. So that's why we're making our own test plan, right? That's why we're doing it the way that we are and not just changing the settings to some arbitrary amount, saying, oh, it works some arbitrary amount, but then when I set the dial to, L instead of M, it doesn't work, right? So that's why we do what we do. Anyway, cool. Was that 1 amp AC or DC for the target? Target test Apply 5 amps. Okay, so you get it to trip. Set the voltage source to provide a target of 1 amp. I think that's AC. If your system's DC, I would test the target on DC. If your system's AC, I would test your target on AC. Something to be aware of. Keep that in mind. Cool. And again, phase angle genuinely does not matter. So our offset current here is 0, right? So our action state is our B channel. This is actually going to be the current that flows through the trip circuit. Our test current is 1 amp. So we're going to go IA. It's sort of a hard thing to explain because you're doing multiple steps at once. So here, before B amount of time, we're at A. IA is steady state. So this is going to be on 10 amps all the time. IB is going to be action. So it's going to be 0, and then it's going to change to 1 after, B amount of time, if that makes sense. And then we're going to run that for, I don't know, 6 seconds. Doesn't necessarily matter. I'm not going to get an operation back to the test set. So I'm going to set this to no op. The test set doesn't care. It's not going to know, right? But I will visually see that the target picks up. That's what we're doing here. So this, I'm injecting current. IB is going to go in 3 to 6. I'm glad I checked. Okay, in 3, out 6. There are, I'm just going to say my test connection is visual. The next time I do this test, if I'm just opening this test plan or whatever, that's going to remind me, hey, I got to look at the actual target. Verify talk target. These are just notes, essentially, to remind the next operator that's using this test plan what we need to do. Okay, so without further ado, got to get it wired up right. Okay. Let's see what happens. It should be the little orange indicator on the left. What do you know? It worked perfect. Cool beans. So that worked great. And obviously the result that we got is literally just the test set didn't see anything. The test set nothing bad happened during the test and it didn't get an input. So this little green check mark doesn't actually mean anything unless you were to visually verify that the target actually worked. Anyway, let's go do the same thing, except now I need to do the instantaneous pickup, which is 22 amps. So instant target. We're going to do the same exact thing. So change some of this stuff around. This needs to be above instantaneous. We're going to go instantaneous plus 1 as a function. And then I don't necessarily want to crank 22 amps through this for a super long time. So we're going to go 15 cycles. That's long enough for it to work. So dump in 23 amps through here. And then 2 to 3, terminal 2 to terminal 3 is our instantaneous trip circuit, right? If we look at our schematic diagram, wherever that is, 27. So we can see our trip circuit in 3 through terminal 2. That's our instantaneous trip. So we have our target element there. So we're going to close the 50 by hitting it with over our instantaneous pickup and then dump current through the instantaneous target circuit. So let's do that. And so it'll trip on instantaneous and then just hold that for another 15 cycles, a quarter second, with 1 amp going through our B channel. It's our action state. So that is, instead of being 3 to 6, it's going to be 3 to 2. Okay, we'll run that. And I want you to look at the instantaneous target right there. Would you look at that? Nothing happened. I got a no op, so I got a happy green check mark on my test macro, but it didn't work, right? Like I didn't get the result that I was expecting. So how do we record that? I mean, you could change this test script to be operate and then it doesn't do it and that shows the fail there. That's not like a great way to do that. again, I always think in the process of like, I got to copy and paste this test plan 200, 300, 400 times and run it again and again and again with different settings. So I don't want to do that. What I want to do is I want to add a specific line in here for test notes, right? So we're going to do data entry step. And this is specific to Protection Suite. There's a myriad of different ways that you could do this depending on what software you're using. I'm going to use the data entry step. So we're just going to call this test notes. Kick it a line here. Call this test notes. My description, just call it test notes. Doesn't really matter. So expected values, don't put anything in there. And then we're going to prompt for a pass-fail rating. And then this, the way the roll-up works is if I had a whole bunch of these and, you know, a whole bunch of prompts for each individual line, or I can actually put in, like, if it's a decimal number, you can put in a tolerance and it'll automatically clock whether or not that was accurate. I do that for meter tests. You might see me do that on another video. And then you can roll up so it automatically, like if any of them fail, the whole test section will fail. Or if one of them goes to warning, it'll all go to warning, however that works. So in this case, we're just going to do text and then prompt for pass-fail rating. And I'll hit run test. And then in my notes, I'm going to say instantaneous target does not operate. And then under my prompt, we click here and we go fail, we go continue. And if we look at that, we go back to our test plan. I got a red check mark or a red X here, meaning this test failed. So overall, when I go to print the report, it'll say this device failed. So if I got a report of like 600 relays or something on a giant site, this one will stick out as, hey, we've got a deficiency on this device. So that's why I do it that way. I knew that ahead of time. The reason I got this relay, I got it for free because I failed this probably 2 or 3 years ago. And, you know, what do you do with a failed relay? You huck it on eBay and hope nobody notices that it's bad. That's kind of jacked up, right? Don't do that. What's next? Oh, so the other function that this relay can do is the instantaneous delay, or the fixed time delay on the instantaneous element. I'm going to show you how we would do that. I'm going to go ahead and enable it. It's disabled right now. I'm going to go ahead and enable it, and then we'll test that as if that was part of our setting. So one moment, please. Everything's all out of focus. Anyway, so let's take this instantaneous pickup test, and we're going to append this down here. So now I have turned on a delay of a 0.2 second delay. That's what we're doing here. So this is instantaneous pickup. I'm just going to put number 2. Obviously, if you're doing this in the field, it would either be enabled or disabled. You wouldn't mess with it like this. If it's enabled, right? So instantaneous pickup with delay enabled. Essentially, all I have to do here, this is the same test as we had before. This is our same instantaneous pickup test. I just made a copy of it, right? All we're going to do here, so we're going to hit it for our 0 amps when our pulse is off, and then we're going to start at 19.8, and then we're going to be off for 15 cycles, and then on 19.9 whatever for a little bit, off, on, off, until it goes up and hits 22. The only difference here is that I need to make my pulse duration longer than my delay. So what we're going to do, I have my Protection Suite set up in cycles. If you don't like it in cycles, you can change it here down on the bottom. I do it in cycles, and I'm weird. It's just it's easier for me. So in the formula bar, if you're going to pull in something, so let's make a setting so I can use that as a function. So protection settings, instant delay is going to be 0.2. So if I did it here as 0.2 seconds, right, I would have to convert that into cycles whenever I use this function later. Or what we can do is there's so many ways that you could program this and have it sort of automated. So if you just turned on switch 8-3, like it'll do it for you. I'm not going to do that. We'll just call it delay and then 0.2 and then bring that in here. Make a note that that is in seconds. We'll go to our worksheet. Instant delay. Our formula is going to be delay times 60, right? Because it goes from being seconds to being cycles. So obviously 0.2 seconds is 12 cycles. So that'll work. So as long as I use this formula, I already know that it's in cycles, which will make my life a little bit easier. And again, you could just set Protection Suite to do everything in seconds or milliseconds and not have to worry about that. Do the conversion however you want. Your mileage is going to vary depending on your application and how you think. If you don't think in cycles, don't worry about it. Anyway, so our pulse duration, we'll use that function. Pulls in 12 cycles. And then let's just do, I don't know, like plus 5 or something like that. That'll work fine. Cool. And we'll run it again. And so our pickup should be exactly the same as it was last time, essentially. Except now we're doing it with the delay on, so our pulses are just longer. The on time is longer. That's all we changed. Which means the test runs a lot longer too, because we've like quadrupled the amount of time it spends being on. Hey, look at that. I think that's the same exact value we had last time. Now we need to test the delay, and I feel like these relays aren't very good at clocking this really short delay, but whatever. We'll double check that in a second. So we're going to go a steady state test, and this is a different macro than we used before. This is going to be a time I, so very similar to my go no go I, except instead of recording op or no op, I'm actually recording a time value. So that my result is going to be a time value. So we're going to go instant delay. What's that? 12 seconds. So that's my expected value, right? And similar to, this is essentially what we do when we do the time over current plot. The time over current plot is essentially this, this time I. See, if I select this current response test with a timer, if I select multi-point test, it knows that we need to do a talk plot. If I do a single point test, it's go, no, go, I, with a timer is time I. Anyway, same exact setup as before. In 8, out 9. Our connections are 3 and 2, which is my instantaneous trip output. Our test points are value, right? We want a time value here. So this is instant delay. I think I already did this, but when you change the macro, it sort of deletes some stuff. Okay. So I think we're good here. Let's, out of the book, I believe it was like 2. I just wrote it down too. Timing is 1 cycle, plus minus 1 cycle, plus minus 2%. So we'll see. If it's within 2%, we're good. We don't have to worry about it. We'll make a custom tolerance if that's not correct. So our offset current 0, offset duration doesn't really matter. 30 cycles for that. That's just how long it's off, and like the timer and the test it's running, it doesn't really matter. Our test current is going to be instant plus 1. There we go. And our max on time is going to be instant delay times like, I don't know, 1.5, something like that. It's pretty quick. So let's run that and see what we get. I feel like doing these in the past, that delay has always been like either right on the edge or totally messed up. So that was 3 cycles late. Yeah, called it. 26% high. So the max tolerance that we have here, all right, if I open a, how do I say this in English that makes sense? Our max tolerance is the expected value, so 12 cycles, plus 1%, which would be 13 cycles, plus 2% of that. Well, 2% of 13 cycles. Sorry, it's killed me. So 13 plus 2% would be times 1.02. That's still 13.25 cycles. You could make the argument that there's like an input debounce timer in the 6150. That's an additional cycle. even at that, this time delay is out of whack. So we've already failed the relay because we know the target doesn't work, and yeah, this relay is bad. I'm glad we pulled it out out of service for the customer. So this one would get a big fat fail sticker. I'm glad we were able to walk through all of the tests that you would do for this. So you guys can actually see how to set this up and how to read the manual and pick through all the options. So, all right, guys. So we have thoroughly beaten this dead horse. Obviously, the relay is no good. It's given its age, the application that it would normally be used in, something like this, it's just best to replace it, get it retrofitted with something new, something more modern, something that's going to last another 20 years. This relay very easily could have been in service for 15 to 20 years, and that's a long service life for a solid state relay with solid state components like that. So the lifespan on these, honestly, the lifespan on the IACs, that IAC is from the 70s, and it passed great. If you saw whatever episode I did the GE IAC relay, those electromechanical relays last a long time. The solid state relays don't tend to last as long, and honestly, the newer microprocessor based relays tend to outlive some of the solid state relays that have been installed in the past, like those old circuit shields. If you see a BBC circuit shield relay, you need to tell your customer or tell your plant manager, hey, look, this thing's on its last legs. Like, we need to schedule a retrofit to get this thing thrown out because it's junk. They're gonna die. I definitely appreciate you guys staying to the end of the video. I know this wasn't a super exciting one, and our relay did actually fail, which I knew it would, but I kept you guys along for the ride, kept it interesting. I ain't got anything else for you. We'll see you on the next one. Appreciate it, guys.